My name is John Schultz, and I'm with Compass Technology Group. Today, we're going to talk about some cool new technology that we can use to measure radomes. This technology includes a new probe that we developed at CTG called the SP2040. It's this black thing right here. It's connected to a new ShockLine VNA that was recently developed by Anritsu right here. And the ShockLine VNA is nice because it operates at high frequency from 20 to 40 gigahertz in our case. So we're going to use this system to measure a radome that we have set up here. And you'll see that we have this radome with a defect where we put a piece of metal tape over there. And that metal tape is going to hopefully show up in our scan, and we'll look at later. And you can see that this system is moving in a raster pattern. So we're going to measure at a bunch of locations and then look at a heat map of that data. So while that's going, let's first take a look at some initial data. You can see we have a dB plot set up here. This dB plot shows the amplitude as a function of frequency. And as I said before, we're using this analyzer to scan from 20 to 40 gigahertz. It starts out at fairly reflective, and then the reflectivity drops to a very low level and then goes back up again. So you can see that tells us that if we were to use this as a radome, we would want our radio or a radar or whatever system we have behind here to be operating at that frequency that corresponds to that null. That's where the system is very transmissive. Now you'll also notice that this null is changing quite a bit as our probe moves around. And that's because the system is very sensitive because we're operating at high frequency. The system, or this radome, was originally developed to operate at very low frequencies where you aren't sensitive to variations. But at high frequencies where we're operating now, we can see very easily differences in thickness and so forth. So you can see as the system is scanning, we maintain a certain distance between the probe and the radome. This distance is the same distance that we use to calibrate, and that's important. It's about 2 inches, and with that 2-inch offset, we have roughly an inch or so spot size of illumination. So we have a fair amount of good resolution as we scan. So let's take a look at our data. You can see our scan is completed. We now have a heat map as a function of y and x directions. Each of these squares corresponds to a different location on our radome. The color of these squares is the amplitude at 35 gigahertz. And you can see we have a color scale here for the different dB levels. You'll notice that we have some orange and red squares that are sort of at a diagonal. That corresponds to the metal tape defect that we put on our radome. You'll also notice that we have some green and some yellow and even some blue color variation on the rest of the radome. Now remember, this radome was originally designed for low frequency. And at low frequency, these types of variations are unimportant and they're not really seen. But we have a very highly sensitive system at mmWave frequencies with this probe and analyzer. And that allows us to very easily detect these types of variations. And in fact, we have a rich data set with lots of frequencies that we can do additional processing on that allows us to then calculate things like delaminations or other types of defects that may occur in radomes from bird strike and so forth. So if you'd like to learn a little bit more about our technology, please check out our website at compasstech.com. And if you'd like to see more about the Anritsu ShockLine series, check out their website at anritsu.com.